Welcome to the last chapter of Math 30-1, the binomial theorem, section 11.3. Oh, and we're going to start off with an investigation. So expand the following out by multiplying. So we have x plus 1 squared, x plus 3 cubed, and x plus y to the power of 4. All right, we can do that. So just using FOIL, so you got x plus y times x plus y. That doesn't seem too bad. So we get x squared, and then x times y, and x times y again, and y squared. Combine like terms, you get x squared plus 2xy plus y squared. Okay, well that was grade 10. And this is also grade 10, so now we just go cubing it. I'm already half done, so it's just going to be x plus y times this trinomial. So x squared plus 2xy plus y squared. And now just distribute the x and the y. So we get x cubed plus 2x squared times y. And then we get y squared times x. And now we'll start distributing the y. So you get x squared times y, and then plus 2xy squared and plus y cubed. Now I do want to change one thing here, just so we're always x then y. I'll just rewrite that as xy squared. There we go. And let's combine some like terms. So you're ending up with an x cubed, and then there's 2x squared here, and there's another x squared here. So there should be a total of 3x squared y. And then here we have an xy squared, and then 2xy squared here. So we end up with 3x squared y, and then the remaining y cubed. Sorry, and this one should be the y squared. There we go. Okay, let's do it one more time. So to the power of 4, well, we already got the cubed version, so we're going to just take that and we will multiply it by x times y. And you're probably wondering, why are we doing all of this? It seems like a lot of work. And it is, but it'll make a ton of sense in a second. So let's just distribute this one more time, or multiply this one more time. So we get x to the power of 4 plus 3x cubed, y plus 3x squared, y squared. And we haven't done the cubed, so x times y cubed is just going to be xy cubed. And now we can start doing the y's. So we get x cubed y, and then plus 3x squared, y squared, and then y times 3xy squared gets us 3xy cubed. And then we get plus y to the power of 4. Combining like terms, so you're going to get x to the power of 4 plus, well, we've got 3x cubed here. It does, and we've got one additional x cubed here. So that means we've got 4 in total. So 4x cubed y. And then we have 3x squared y squared here, and another 3x squared y squared here. So we get 6x squared y squared. And in our next one, we have an xy cubed here and an 3xy cubed here. So a total of 4xy cubed. And then we only have one y to the power of 4. Now it's really hard to see the pattern when you've got them all laid out like this. So I'm going to write this in a very specific way. In the first line, I'll just put the trinomial. So you're going to go x squared plus 2xy plus y squared. In my second line, I'll do this polynomial. Now, I'm going to write it a little bit weird. You're going to see it's a little bit off center of what you might expect. So 3x squared y plus 3x y squared plus y cubed. And then finally, I'm going to write this last polynomial. So same thing. I'm going to just write it. Kind of look odd right now why I'm putting it in this order. 6x squared y squared plus 4xy cubed plus y to the power of 4. So this might be a good time for you to just stop the video and see if you can see any patterns here. Okay, so hopefully you took a chance to stop it and look. So things I notice, if you look, the x's all have a coefficient of 1, 1, 1, and it looks like the 2, then 3, then 4. Same thing on the right side. The y is coefficient is 1. The exponent is going up by 1 as well. So that's some patterns. Maybe a little less noticeable, but if you look, this coefficient is 1, this coefficient is 2. Well, 1 plus 2 is 3. And then same thing here, actually, 1 plus 2 is 3. And if we go down, the pattern actually holds. So coefficient of 1, coefficient of 3 here. Well, 1 plus 3 is 4. And then here, 3 plus 3 is 6. Oh yeah, this holds the whole way through. This little triangle idea that we've kind of made actually holds forever. Some other little things you'll see as we go for each term, the exponent is going down by 1 as the y is going up by 1. And that pattern holds every time as well. So again, 4, 3, 2, 1, 0. So there could be an x to the power of 0 here. We wouldn't write that. That's just equal to 1. And then the y is increasing by 1 each time. So those are some things to be looking for. So we call this pattern Pascal's triangle in binomial expansion. So you can see kind of a nicer example written out of what we already showed. And it also goes to a binomial with an exponent of 0 and 1. Now there is something that's really important on this page though, is our row number does not match our exponent. Okay, so our row number is always one more than whatever the exponent is. So for instance, if I had an exponent 2, well, that's actually going to be the third row of this triangle. And why that's helpful is I can actually just write the triangle out without any of the x's or y's. I can just go 1 and then 1, 2, and then you can start making it. Well, here, this just continues 1, and then 1 plus 1 is 2, and then 1 plus 2 is 3, and then this pattern just holds forever. So you can make this triangle without having all the x's and y's. And we can use that to figure out what the coefficients are of an expansion of a binomial. So if I asked you, hey, what's x plus y to the power of 5 or 10 or 20? Oh, how bad would that be to have to do x plus y times x plus y times x plus y 20 times? That'd be awful. But Pascal's triangle says there's an easier way. But mathematicians found even a better way yet. What if we used some other method to figure out, well, what's actually in the row? Because maybe I don't want to draw out 20 of these triangles, like 20 rows. Or what if it was 100? Oh, it'd be painful. Well, you know what? You don't have to. You can use combinations. And so, for instance, if I type in, let's look at this fifth row here, 5 choose 0, well, that's equal to 1. And if you don't believe me, we can go 5 choose 0. So we end up with this. Well, 0 factorial is 1, and 5 factorial divided by 5 factorial is 1. Well, here, 5 choose 1 is going to be 5, and 5 choose 2 is 10, 5 choose 3 is also 10, and then 5 choose 4 is 5, and 5 choose 5 is 1. And actually, we can do this for any row. Like you can start in row 20 and go 20 choose 0. That'd give us our first coefficient. And then 20 choose 1. That's our second coefficient in that row. And you can go on and on doing that. So a much more efficient way than maybe drawing out the triangle, or much, much better than doing the binomial expansion like x plus y to the power of 20. Oh, that's going to take so long.